The goal for the next few days is to give you a quick demonstration of what we will do in the January course. Now, I am assuming that we have participants who have no background in Python programming. Yes, I will share my screen. For some reason, I have two windows. So if I close one, let me see if I close one because I have feedback. Okay. Can everybody still hear me?
Yes, sir. We are.
Oh, fantastic. Fantastic. Okay. 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 So just for a show of hands, how many of you have some background in Python programming? A couple of yes, no would be great. Just to get an idea, how many people I have who have some background in Python programming.
Hi, sir. Sorry for interrupting.
Right.
The screen is not visible. Have you
Okay,
shared your
okay, okay.
screen? Oh, yes, sir.
Hang on a second. Let me share the screen up here. Right. So one more time, just a quick show of hands, perhaps. Uh, how many of you have some experience in Python programming whatsoever? Can they hear me? Can people hear me?
Yes, sir. Yes, sir. You are audible.
Okay, 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 okay. All right. So if you don't have so because I can't see your responses for whatever reason, I am going to so hands were raised for people who don't know Python, right? Okay, okay, okay. Thank you, Mr. Tajuddin. So I will still start with the basics, and I will, we will figure out where things stand, where we can get some more responses in. So the way we are going to do it, obviously, you have to install Python in your computer, and I have already installed it. But during the course, we will tell you how to do everything. So for the next today and tomorrow, please sit back, relax, and just see what can be done. I will go from the very beginning, and I will quickly go through a few examples today, and then tomorrow we'll go through some more examples that are slightly more complex. The plan for today is to have basic Python programs where you solve some simple models of geological problems, generate a few plots, work with some data. And tomorrow again, more plotting, more data handling, and using geological models, geological libraries. So obviously, since you have signed up for a Python course, you have heard the name Python. Python is a high-level programming language, and it was developed by Guido van Rossum in the 1980s, 1987 to be specific. And since then, Python has become extremely popular in the scientific community as well as in other communities. Now, in the recent days, for the last few years, Python has made huge inroads into the geoscience community. Particularly, there are several research groups that work with Python. There are specialists in industries who use Python to work with their problems and solve models. Now, the problem is, or the issue at hand is, general geology students or professionals don't necessarily have a Python background. Unless you really have to, you are forced to learn it, and so on and so forth. So the purpose of this particular course in January is to kind of alleviate that gap. And PEA has done a wonderful job to provide this platform to do this introductory show and tell for you to understand where things can go. So a computer programming language, in very simple terms, has a few keywords and a bunch of grammar, which is stored in the program's kernel. And our job is to write some commands, which are programs, which are a series of commands to perform the task at hand. Okay. So that is what we are going to do. Okay, so I'm going to go ahead and get started with writing some very simple codes. Please, in the chat, ask me if you have a question regarding what you are doing. But all major Q&As, I think, will be best left for tomorrow once you see what we cover today. Okay, so without further ado, I am going to dive in and start writing some code. Now, what I have opened up is called a Jupyter notebook, where it is easier to teach, where I can essentially show you line by line what is happening, and then execute that line, and you can see the results of that line. Okay, I see there's a couple of messages saying they have basic backgrounds and so on, which is great. So please bear with us if this is too simple, because I have to keep in mind the entire audience. And based on the feedback, we can, switch things around. So the very first thing for any programming language is to be able to print something. Okay, so one of the easiest things to do in Python programming is to print something, and it's a very straightforward command. You use the print function in Python. Print is the command and also a function. The function, it is a function because you have to pass an argument into the function. So if you go back to your good old mathematics class, when we learned f of x, where x is the argument to the function f within f parenthesis. So it's the same idea here. So if I want to say hello geology, and if I execute this line of code, I can see the result right up front. And this is one of the advantages of using a Jupyter notebook, where I can execute individual lines and we can see what we are doing. Now, next to formatting, the next piece of information we want to learn about are variables. The reason we want to learn about variables is because we want to work with, we want to find unknown quantities. And for that, Python follows very closely with the concept of algebraic linear equations. And you will see that very quickly once I write a couple of very simple programs. So let us start off with how many types of data there are. So variables obviously contain data. Variables contain data. Now, there are several types of data, namely int, which is integer, float, which is decimal, then complex, which is complex numbers. Then we have what is called bool, which is Boolean. And obviously we have our good old friend string, which is just alphanumeric data. Now, in addition to data, we also have what is called data containers. And we will cover a few of those perhaps today, later. and then we'll go on from there. Okay. Now, with data also, we have some basic mathematical operators for Python. Basic math. And these are your standard plus, minus, multiplication. There is no multiplication sign per se, which is, this is the star, and then you have the division sign. Now, there are other things that can be done. There is another one, this the percent sign is also there. This is called the modulo operator, and we'll learn about modulo operator, what is the use. Briefly, the modulo operator's function is to return the remainder after division. Okay. So these are our fundamental mathematical operators. Now, one might often ask the question, what about powers? Now, for power, there is a function itself, but if you don't want to use the function, so anything to the power of anything can be written by double star. Okay. Again, if I'm going too fast or if this is way advanced, please let me know. I mean, this is very elementary, simple stuff. Okay. So actually, let us start off with a very simple geological model, and we are going to do some very basic calculation. So as of now, you can see that I have been writing comments. So in Python, you can use this pound sign or hash key, whatever you are comfortable with saying, as writing a single line comment. So for example, if I started writing, hello, how are you? And then press enter and then say, I am fine. You see, there is a difference. So multi-line comments are not supported by the hash key or the pound key. For multi-line comments, we have to use in Python what is called the triple quotes. And I typically write it this way so that I know there is a starting and there is an ending. You don't have to follow that, but this is what I prefer. It's just good programming practice. And I say, we are learning Python application in geology. So, you know, you are allowed, then you can write these comments, and obviously comments become very important in your program, obviously, because it helps you keep track of what you are doing as a beginner. Even for people who have some basic background, it is very helpful when you can kind of come back to your program a couple of days or a couple of weeks or a month after you have written it and quickly peruse the comments to figure out, this is what I am trying to do. Okay, so let us try and write our geological model. Here is our geological model. We will try to calculate the pressure at Mr. Khan, the recording option is up to Miss Upadhyay and PEA. So they will respond to your thing, and the course is already being recorded by them, I believe. So I think somebody from PE can respond to that. Okay. So our geological model is to calculate the pressure at any depth. Now, obviously, you know how this formula goes. P equals depth times density times acceleration due to gravity. So let us see how we write these kinds of programs. Okay, I'll show you the simple way first, and then a little more complicated. So now one way is for us to assign certain numbers to our to our parameters like depth and density and gravity and so on and so forth. Now, one of the challenges of scientific programming is Python doesn't care about the units, because it doesn't want to deal with units. And if you want it to deal with units, you have to use a library. But for now, we will manually keep track of the manual track of our units. So first of all, we are going to use a value of G of 9.81, and then this is how I keep track of my units for whatever I am typing. Okay. Now this is very helpful, because Python will read this line and ignore this part because it is after a pound sign. Now, because Python ignores this after the pound sign, I'm fine writing this over here. Okay. Then let's say I use a density value of, remember, we have to use kilograms per meter cube. This is a big problem in programming. You have to keep track of the units and the conversion and all of that. You can make Python do it, but you will have to instruct those things explicitly. So let us say we say the density is 3200 kilograms per meter cube. Okay. And then we can say that the depth is, let's say, 200 kilometers. Now, you will obviously notice that kilometer is not the SI unit. We will take that into account when we calculate pressure. So then we say P, or pressure, is equal to just the product of these different variables. So I can say that times 1000. Remember, because 1 kilometer is 1000 meter, so I have to do that. Then I just simply type density times I do that. All right. And then what do you think should be the unit? The unit for this is obviously pascals. Okay. And then we can say print depth percent D kilometer is percent point F pascals. Please don't worry, I'll explain everything what I am doing. Just let me write the code. Okay, so now if I run this particular piece of code, it tells me that pressure at depth 200 kilometer is this. Now, what I have already shown you are several things here. Let me walk you through them one by one. First of all, variable names must start with an alphabet. Okay, you cannot start a variable name in any other way. Variable names can have numbers and special characters. Okay, but after the first letter, which is after the first letter, which has got to be an alphanumeric alphabet. Okay, it cannot be anything else. Okay, so those are certain rules. There are certain standard rules in Python, and then there are rules that programmers have developed as they kept on programming to solve their problems. Now, what I have done over here is try to write this out in a fancy manner. Now, you will see I have used the modulo operator inside a string. So strings are written as quotation marks, within quotation marks. And the percentage in that context sort of acts as a blank. So Python is going to read pressure at depth, then keep a blank, continue, again it reaches a percentage, put a blank, and complete writing that text. But what goes inside those blank? Whatever goes inside the blank is written like this. You put in a percent sign outside the quotation mark, and then within parentheses, you report the order in which the variables that will go into these blanks. So for example, in this percent D, depth is going to go in there. But you will say, what is this D business? This D business tells Python that in this blank, the number that is going to come in is an integer. See, this is 200. Okay. And over here, I have 0.2f, which means this is going to be a float or a decimal value, but that decimal value will have 2 decimal places after the point. Okay. So that is how I have formatted it. So this kind of comes out as an answer to your problem. Okay. Instead of just saying the answer is 62784 followed by 5 zeros, which could be anything. Here you have a very nice way of printing out what you are trying to say. All right. Now, there are some serious challenges in this particular program. What are those? Those challenges are that I have made several assumptions which violate the laws of physics. First of all, you all know Earth is not a one-layer planet. It has multiple layers, and therefore, and you also know because of accretion, the density also varies with depth. All right. Now, acceleration due to gravity also changes. Okay. Now, I am not going to show you the full complex code, but I am going to show you a brief of what is going to be taught in the main course. I'm going to share a picture with you, or rather an equation and a little bit of, and we'll discuss this a little bit. Okay. So let me stop this share or new share, and I'm going to share this screen now. Okay. So now in this particular table, what I have is the different layers of the Earth from the center. Okay, these are the different layers: inner core, outer core, lower mantle, upper mantle, crust, and the radius from the center of the Earth to the top of the Earth, to the surface. Okay, and then I have also put in the thicknesses of those particular units over here in thickness in kilometers. Okay. Then I have put in, and this is the radius length. So starting from 0, inner core ends at 1220, outer core ends at 3479, lower mantle finishes at 5650, so on and so forth. So the thickness of each layer is given over here. The density of each of the layer boundaries are provided over here at the bottom and at the top. So for that each layer, you have a density at the bottom and density at the top. So now we have a scenario where we can generate a linear gradient of the density inside individual layers. Okay, and then we can use that to plot out individual densities inside any depth inside the Earth. Okay, so essentially you are able to recreate the PREM model, which is the primitive relative Earth velocity model, from data like this. Now you can argue, well, I don't want to put a linear gradient. I want to put an exponential gradient. Be my guest. You are more than welcome to do that, except your boundaries will be defined by the density bottom and density tops. Okay. And then we will actually write some really complex code here, which involves writing a little bit of code for integration and things like that. Again, I will walk you through everything during the January course. Okay. Now, to kind of give you a bigger taste of what's at stake or what's in store, let us go back to the work I was showing you over here, and let us modify this program and make it a little more challenging. Okay. Now, in this particular program, what I am going to do is I am going to say the following. So I'm going to create a new model. And in this model, I am going to say we have a crust, mantle, and core. Okay. Now we'll say the average crustal thickness is about, I don't know, 50 to 70 kilometers. So let's say 50 kilometers with a density of about 2,500 kilograms per meter cube. And we will assume we'll still keep things simple, and we will say that acceleration due to gravity is 10. Doesn't have to be 10. You can put the more accurate value of 9.81. It makes no difference. So then I can essentially write this out for the mantle. I'll obviously change the numbers in a second. The mantle goes up to, let's say, at a depth of about 2,900. So I would say the thickness is 2,850. Okay. And the thickness of the density is typically, 3,200 or 3,500 kilograms per meter cube. We keep the acceleration the same. The thickness for the core, I know that the core goes up to a depth of about 6,400 kilometers. So if I subtract 2,850 from that, what do I get? Let me open up my handy dandy calculator. See, I don't try to remember everything all the time, because the purpose is for us to do problem solving, not memorization. So we try to keep things at, where we can easily calculate them. So 6,400 minus 2,850 gives me 3,550. So how about that, right? And then the density over here is about 12,000 kilograms per meter cube, and so on and so forth. Okay. So now if I wanted to calculate the pressure at the crust mantle and mantle core boundary, this is relatively easier. So like, for example, we can do pressure at crust mantle boundary will be equal to 50 times 1,000 times 2,500 times 10. Okay. Again, I have to keep in mind that the unit will be in pascals. Okay. Then the pressure at the mantle core, this one, you have to be a little more careful. The reason is that it is going to be the pressure of the crust plus the material of the mantle. So then that will be P underscore Cm plus, then I have the thickness as 2,850 times 3,500 times 10. And again, this will be in pascals. Similarly, pressure at the center of the earth will be P underscore MCO plus. We can do this very easily now. 12,000 and times 10. So again, we have our unit as in pascals. Now, this is all fancy and good, you know, and obviously we can print. Boundary percent P pascals, where I just use that. PM. Then it's a matter of copy pasting. We'll do a lot of copy pasting of our previous lines of code in the course as well, so we can speed up what we are doing. Okay, so then we can say mantle core boundary is this is center is PC. Okay. Now, you know, and there you go, you have the calculations right out there. Okay. What I want to, so hopefully this sounds relatively straightforward to you. Now, the next thing I'm going to do is show you a very quick example of how to ask for input from the user, because as of now, we have already provided every piece of information. Okay. So to ask for an input, let's say I want to make these thicknesses inputs. Okay. So what I'm going to do is actually copy this entire piece of code, copy it and paste it over here. Okay. Except I am going to ask for 3 inputs. The first one will be thickness of the crust. And I will have to ask for now I am going to ask for integer value. We can obviously do float, that is no problem. There is no problem doing that. But for the you know, clarity and to show you an example, we are actually not doing the course per se right now. So enter thickness in kilometer. Okay. And then again, I'm going to just copy this. And I'm going to say thick mantle. And thick core. Okay. All right. And then we will just in place of that, I will put in the variable name. Okay. Instead of that, I will put in this. Instead of this, I'll put in that. Okay. Now, if I run this code, you have the advantage of varying your crustal thickness to whatever model you are using, or whatever model you are trying to solve. Now, so let's put in 70. Okay. Then it is going to ask for the thickness of the mantle in kilometers. Let's say I put in, I don't know, how much shall I put in? I say I put in 2,500. And then let's say I put in 3,500. And there you go. Now you would jump up and say, hey, hang on a second. These values don't necessarily agree with us. It doesn't have to. And that is the beauty of that. If you have any seismological data that tells you the layers of any planet, you can code that. It doesn't have to be a 3-layered planet. You can have an n-layered planet and you can write appropriate code to solve that. Okay. So in the actual course, we will, in the longer version of the course, we will spend some time showing you how to measure or how to calculate the pressure at intermediate depths, like between layers, where things get a little more complicated. Then we are going to show you how we can use logical conditions to kind of play around with the program to answer exactly what we want to be shown in our model. Okay. So let me show you. I'm going to jump through a few things because, again, in the interest of time, because I want to show you some capabilities so that you understand what you are going to get. Is I'm going to show you some data analysis very quickly. I'm going to show you some data analysis because, you know, at the end of the day, after a while, these procedural programmings are good to know in the beginning, but at the end, you are all trying to do data science analysis, and that is very important. So I have some data with me, and I don't know if you can see this, but let me show you. Where is it? I have too many things open. Give me 1 second. Let's see here. Okay, where it is. Yes. So if I may share the screen with you, I have a folder called PEA course on my computer's desktop, where I am running this untitled Jupyter file, and it contains some checkpoints. That is not important right now, but I have some data. Okay, I have some geochemical data that I want to show you. Okay, this geochemical data is for volcanic rocks, and in the data in this Excel spreadsheet, I have 2 sheets. The first sheet contains the major element concentrations of individual samples, and the second sheet contains the trace element concentrations. Now, there are about 370 samples, which means 370 rows of data, and 37 columns for the trace elements, because there are 37 trace elements. Okay. So again, let us go back to the code that I was sharing with you, and let us try to bring in this particular code. Okay. So what I'm going to do is for database analysis, particularly spreadsheet data analysis, we have a library called pandas. So we are going to import pandas as PD. Okay. The reason I am doing it as PD is to kind of help reduce my typing time. So instead of typing pandas all the way, every time, it is much more easier to type PD dot whatever something. Now this helps me with extracting data from an Excel spreadsheet. So how do I do that? Now I know I have an Excel spreadsheet. If you have a CSV file or a text file, the command is slightly different. But for now, let us look at how I extract my data into a pandas data frame. A data frame, in simple terms, is your Excel file as you see it. Okay. So I am going to type df equal to pd dot, which means call the pandas library. In the pandas library, use a special command called read underscore Excel, because this is an XLSX file. If you had a CSV file, you would have simply written read underscore CSV. Okay. If it was a text, you would just say read underscore text or TXT. Okay. And then because the data, as I showed you, is in the same folder as this Jupyter notebook, I am going to just say the name of that Jupyter XLX file, which is geochem underscore data. Geochem underscore data. Okay. Now, remember, I told you that this geochemical analysis data has two sheets. The first one contains major elements, and the second one contains trace elements. So I am interested in the trace elements. So I'm going to put a comma and pass another additional command that says, not tab, it is called sheet name. Sheet underscore name. Again, we will in the detailed course, we'll go through what are the different options and so on and so forth. And again, I'll teach, we'll discuss how to read documentation and all of that. Okay. So sheet name equals geochem underscore data dot XLSX. Okay. So I want to put a geochem data dot, sorry, XLSX. My apologies. I should have not written that. I should have written SUPP underscore traces, because that is the name of the sheet in which trace element information is there. Okay. Now I am going to execute or run this code, and you will see that it takes a little bit of time for pandas to read Excel files. CSV, ASCII files, text, it absorbs it very quickly, because in this one you have additional code where Python is actually going into the Excel file, sees and identifies there are two sheets, and then looks up the sheet that you are interested in. And so it takes a little bit of time. So it's already done. Okay. Now we are going to make a very simple plot of some certain things. But before I do that, let me show you what does this contain. So if I say df head and I execute this code, I get some information. What information do I get? First of all, I get what are the column names in the spreadsheet. Okay. So you can see it says that there are 37 columns. Now it's not showing me all the columns, so but it is saying that there are a lot of columns here. And however, if I what did I do? Now, another thing to look at this data frame is called df.info. If I do a df.info, this tells me all the details. What kind of data set is this? So this is a pandas data frame. See, it says data frame. I want you to know that. And in a data frame, you have rows and columns, right? See, the range index tells you how many rows are there. Okay. And it says that there are 370 rows going from index number 0 to index number 369. This is one of the quirks of Python. Again, we'll discuss that at an appropriate time. Now over here, it tells you all the names of the columns. It tells you how many non-null numbers are there. So for example, I told you there are 370 rows. But if I scroll down, you will see there are a number of situations. So the column for lutetium has one analysis missing. The analysis for lead has 2 data points missing. Okay, and these are normal. Your data is not always going to be fully populated. We will learn how to handle that, so that if you run any statistics on these data, so that your statistics gives you an accurate answer. All right. Okay, so now let us go ahead and create a very simple plot. To create the plot, what I am going to do, I am going to use another library called matplotlib. All right. Again, this takes a little bit of time, so I'm going to do that and wait for it to run and put it in its memory. Now it has done that. Now what I'm going to do, I am very interested in looking at the zircon versus thorium plot. Okay, so I am going to plot the zircon data in the x-axis and the thorium data on the y-axis. So the first thing I have to do is I will extract the zircon data that is going to go in my x-axis from this table. So I am going to say df dot column name. Okay, so if I say x equal to df dot zr, what Python is going to do is go into the data frame, go over to the zircon column and extract 370 non-null float data into its memory. Okay. Similarly, I am interested in the y-axis. It is data frame dot thorium. Okay. Very straightforward. I am just extracting the data and sticking it to a variable to store them. Okay. Now I am going to plot it. So for plotting, we are going to use the figure and axis for plt dot subplots. Okay. This is a matplotlib command that internally generates a frame in the background on which you are going to plot the data. Okay, figure is the full name, and axes are what you are going to plot the data on. Okay, and we are going to call this axis over and over again to plot things over there. So let me show you a simple scenario where I can say ax, the axis, dot scatter. Okay, and then I am going to put in my xy data, and that's it. That's all I have to do. And if I execute this code, after a little thinking, Python generates a plot for you, where unfortunately we don't see any titles or labels. But one thing is very clear from the very get-go, that this entire data has some sort of a trend. And the geochemist among you will jump up in joy and says, okay, or any geologist among us will say, okay, there is some relationship over there. And it is entirely possible to write another piece of code to calculate the correlation coefficient and generate the equation of a straight line from this data. Okay. All right. So now let us do some cosmetic change. So let us put in some labels and change some colors, and let us change the shape of the plot. Okay, so we are going to say fig comma ax equals plt dot subplots. Then we are going to say ax dot scatter x comma y comma. So let us say I want the symbols to be triangles. So I will say marker equals this upper arrow, And let's say I want the triangles to be red. Color equals red. Now it doesn't have to be red. You could put any color you want. Now, if there is some weird color that you want to put in, or interesting color that you are interested in, you can always go and find the hexadecimal representation of a color from Google Color Pick, and then put in that hexadecimal hash key, and Python will accept that. Okay. Now I have done that. Now I am going to say ax dot set underscore title, and then I am going to plot my title of zircon versus thorium plot for volcanic rocks. Next, axis dot x label oh no, set x label, set underscore x label, and then I can say zircon in ppm. So you can put the units there. Then I can say also we can say over here label equals zircon y over thorium over zircon, and now this is a ratio, so there is not going to be any units over here. Okay, now I can then say axis dot set underscore y label, and I can write thorium in ppm. Okay, and then I can say what else can I put in? I should perhaps call the axis legend ax dot legend and x dot grid. Okay. Now, if I do all of this, let us see what happens. Okay. So let us execute this code, and you will see immediately you have a publication quality plot where you have zircon versus thorium plot for volcanic rocks. You have the data has been plotted. You have the labels over here. The legend is shown over here, and the grids are shown. Now, the last thing I want to show you is how to save a figure like this. Now, and it is going to save in the same folder that this particular Jupyter notebook is in. There are ways to save it in a folder of your choice. So, for example, I would say plt dot fig. Now, you can save it in all different formats. I will save it in PDF format first. I will save this as zircon underscore thorium binary plot dot PDF. Okay. See, this PDF, it will read, and so you can put here PNG, TIFF, or JPG. I think it doesn't do TIFF, but PDF gives you the best resolution. So if I again execute this and wait for it to show up, okay, so this has been saved. So let me show you my screen again, where I can show you this this whole thing. So if I go to my folder, you will see automatically there has been a PDF file that has been created that says zircon thorium binary plot. So if I open this plot, again, I have to share my PDF. So please give me a second for it to open up. New share the PDF. Okay. So you can see, let me zoom out a little bit to 100%. Okay. And you can see you have a very nicely scaled plot. The size is scaled to A4. The beauty of this is you can zoom out as much as you want or zoom in as much as you want without losing data quality. Okay, so you can see that I can zoom in and none of my plot or data is pixelated. See, nothing is pixelated. So if you want to do some additional, writing or annotations that you find challenging to do in Python, you can do that in any graphic editor software. So for example, you can take it to Illustrator, Inkscape, Photoshop, or Canvas, or whatever software you use for graphics editing. Okay. So obviously in the main course, we will have the opportunity to go into details of how to do different kinds of labeling and things like that. I think this is a good place to stop, where I think Mr. Nikhil will have some things to say. And so I will hand this over to Nikhilji and others to take over, please. Nikhilji, are you there? Hello. I